Hi everybody, in this set of videos, we're going to keep working with functions and actually learn how to combine them and put them together. So we're going to talk about combination of functions, which means how to add, subtract, multiply, and divide functions. And then we're going to talk about composite functions, which is when we actually plug one function into another. So that's what we're looking at in this section. Before we get there, though, we do have to discuss domain. So we've talked about domain already in class, but really just to kind of talk about it again, make sure everybody's clear on it, and also look more at how to deal with it with a function, particularly when we're not graphing. So if a function f does not model data or verbal conditions, so meaning that there's no extra restrictions on it, its domain is a larger set of real numbers for which the value of f of x is a real number. So typically, we exclude from a function's domain real numbers that cause division by 0, and real numbers that result in an even root, such as a square root of a negative number. So we don't want to have division by 0. That's never okay. And I know we can have imaginary numbers, but when we talk about domain, we don't include imaginary numbers. It's only real numbers. So we don't want to have any negatives inside our square roots either. There are additional domain restrictions out there, but these tend to be the two main ones, at least for the functions that we are most often dealing with. So those are the two that we're going to focus on. So in our first example, we're going to find the domain of each of these functions. And if you look at the first one, you'll notice that there's nothing really going on there. I see x squared minus 7x. I don't see any roots. I don't see any denominator. If I think of this, this is actually just a quadratic function. So it's going to be some sort of U-shaped graph. And there's no issues going on. I can plug in any x value I want, and I can get an answer back out. So something like this has a domain of all real numbers. And in interval notation, we write that as negative infinity to infinity. So we're just saying that everything is included here. Now, in our other examples, we're not going to have that. So in example B, we do see we clearly have a denominator. So we do need to make sure our denominator is not equal to 0. So I'm going to set that denominator actually equal to 0, and I'm going to solve so that I can figure out where those bad values are. And if you look here, this is a quadratic, right? It has a square. So I could use the quadratic formula if I wanted to. This one I could also factor. So we could factor here, and that works too. So either of those two methods would be good ones to use here. I'm going to factor because I find that to usually be a little bit faster. X squared is just x and x. And then for 3, it's 1 and 3. And it's just a matter of figuring out the positive and negative signs. So I'm going to put the negative on the 3 and the positive on the 1. This will give me a negative 3 when I multiply. And then on the inside, when I multiply out, it'd give me a 1x and a minus 3x, which is minus 2x. So it would match if we check. Do remember that when you're factoring, always check, even if it's a mental check where you physically FOIL everything out. You don't want to go on and then realize you have the wrong factors and get the answer wrong for something like that. Once I have my factors, then I can set each factor equal to 0 and solve. So here we subtract 1. Here we add 3. So those are the two values that make the denominator 0. So these are the two values that we want to exclude. We don't want these values. These are the bad ones. So our domain is a set of all x's such that x is not equal to negative 1 and 3. That's our set notation answer. For interval notation, we want to write it so that we skip over the negative 1 and the 3. So we go from negative infinity to negative 1. Then we go from negative 1 to 3, and then we go from 3 to infinity. By using parentheses, remember, we're not including those end values, so we're skipping over them. For example C here, I don't have a denominator, but I do have a square root. So I do need to make sure that the inside of my root is greater than or equal to 0. And again, that's only valid for even roots. Square roots, fourth roots, sixth roots, and so on. So I set 3x plus 12 greater than or equal to 0. This is a linear inequality. We've seen these before, so we can just subtract that 12 to both sides. And we can divide by 3. And we get x is greater than or equal to negative 4. So our domain here in set notation is all x such that x is greater than or equal to negative 4. Or in interval notation, we're going from -4 to infinity. But remember, because you have equality here, you're going to use a bracket instead on that -4. And then finally, for our last one, here we sort of have a double issue. We have a denominator and we have a root. So we have two things we have to watch out for. So we need to make sure that the inside of the root is at least 0 and that the denominator is not equal to 0. So think about putting these two ideas together. If I have a root in the denominator, it has to be 0 or bigger, but I don't want it to be 0 because then that would be an issue in itself. So what I'm going to do instead is make sure the inside of my root is strictly greater than 0 in this case. That would keep the inside of the root positive, so I don't have any negatives there. And it also makes sure my denominator is not 0. So I subtract 14 from both sides. I'm going to divide both sides by -2. Remember that when you divide by a negative with an inequality, this sign has to get flipped. So it's going to end up being x is less than +7. So our domain here are all x values such that x is less than 7. Or in interval notation, we're going from -infinity up to 7. And because it's strict less than, we're going to use a parenthesis there to show that the 7 is not included, right? If I plug in 7, it would make that denominator 0. So we don't want to include that end value here. Okay, so now we've reviewed domain. And again, these are the two main issues we tend to look for, at least at this point. And we're going to talk a little bit more about the algebra of functions. So you actually can add functions together, subtract functions, multiply them, and even divide them. And don't overthink it. When it says notation like this, f plus g, it really just means add function f with function g. When you see f minus g of x, it really just means take function f and subtract function g. Fg is f times g, right? Because there's no symbol. So we multiply those two functions together. And f over g means to divide them. So what's going to happen here is the domains are going to basically be the same as the original functions, but put together. So if f and g are function, then the domain of f plus g, f minus g, and f times g is just the intersection of the two domains of the original function. So it just means that the x values have to work in both functions, right? So you can't just have that it works in the f but not the g. So you intersect or kind of combine together the two original domains. The same thing is true for f divided by g, but you also have to make sure that we exclude x values in which g is 0. So you may have an additional exclusion there because now you're dividing by g, which you weren't before. So you may have to also add in additional exclusions for your domain with that division. Let's do some examples so you can see this in action. All right, so I'm going to do one example of each style of the adding, subtracting, multiplying, and dividing. And there's all different kinds of functions you can use here. So I have a linear function and a quadratic, but you'll see as you go through the textbook and assignments as well that functions can have roots, they can be cubic, they can be absolute value, etc. So you're going to look at all different kinds of functions, but the same basic ideas are still there. And again, we're not going to focus on domain just yet, although I'll talk about it a little bit afterwards, but we're really just focusing on the algebra piece, actually simplifying. So when we see f plus g, you're just going to take your f of x function and add it with your g of x function. So my f of x function is right here. It's 2x minus 1. And my g of x function is right here. It's x squared plus x minus 2. Now I'm using parentheses just to show you the two functions. It's actually not necessary for addition, but you do need it for your subtraction and multiplication and things. So it's just a good idea to start with the parentheses, and then you can decide if you need it afterwards. Here we're just adding, so there's nothing to really distribute here. I can rewrite it like this, and then I'm just going to combine like terms. So I have x squared, I have a 2x plus x, which is 3x, and then I have a minus 1 and a minus 2, which is minus 3. So f plus g of x is x squared plus 3x minus 3. All right, let's do the next one here. Here we have subtraction. So you're just going to go ahead and subtract those two functions. So my f function is 2x minus 1, and my g function is x squared plus x minus 2. Here I do have a subtraction, so I am going to have to distribute here. And then I'm going to combine like terms. So I have negative x squared, 2x minus x is plus x, minus 2 plus 2 is plus 1. And whenever you're doing these, you're just going to simplify as much as you possibly can. So here I do have some like terms I can combine together. Sometimes you can't do much. So if you're, if you have a square root function or an absolute value function, there may not be much that you can actually simplify. So you just do whatever you can. Here I see multiplication. So you're going to take the f of x function and you're going to multiply it with the g of x function. The f function is 2x minus 1. And the g function is x squared plus minus 2. Now here I have to actually multiply and distribute everything out. So it's going to take a little bit of time, but we can do it. I start with the 2x and I multiply through. So 2x times x squared is 2x cubed. 2x times x is 2x squared. 2x minus times negative 2 is negative 4x. Here, negative 1 times x squared is negative x squared. Negative 1 times x is negative x. And negative 1 times negative 2 is positive 2. Now I'm just going in, I'm double checking all my work that I have done out to the side, making sure I'm not making any little mistakes. I'm going to combine my like terms. 2x cubed comes down. Let's see, 2x squared minus x squared is just plus x squared. Minus 4x minus x is minus 5x, and then plus 2. So f times g of x is equal to 2x cubed plus x squared minus 5x plus 2. And then finally, for the last one, you're just dividing. So you're going to do f of x divided by g of x. There's often not too much you could simplify here, but we'll try. So f of x is 2x minus 1. G of x is x squared plus x minus 2. Let's see, I can factor this one, so you would see if you could simplify it all. I can factor the denominator, so we could check that first. So this is x and x. And then if I have 2 and 1, it would factor this way. And I could see if I could cancel any factors in common. I actually can't here. So I know I see an x minus 1, but because this has a 2 with it, it's not going to cancel out. I can't just cancel some of this. This is actually like one group stuck together. So we try, but there's really nothing that we can do to cancel here. So this is just my final answer. Now, I do want to talk a little bit about domain for a second. I know this question didn't specifically say find the domain, but I think we should add it in. So to find the domains, you want to start with the original functions and think about their domains first. So in both cases, I don't have any denominators and I don't have any roots. So there's really no issue here. So both of these have domains of all real numbers. And the way we can write that, of course, is negative infinity to infinity in interval notation. So for f plus g, f minus g, and f times g, you're just going to combine these two domains together. Now, they're both all real numbers, so there's nothing to really combine there. And what happens is your domain in each of these first two cases is going to be the same, right? There are no restrictions in either case. If there were restrictions, so let's say this one had a restriction where you couldn't use the number 2, and this one had a restriction where you couldn't use the number 3, then all your domains would have restrictions on 2 and 3 together. So you just kind of put all those restrictions together and exclude everything. But here I don't have that. Everything works, so it's fine. Now, the only difference is this last one. And again, for F and G, it's all round numbers, but the problem is I kind of messed it up here and I divided. So now I have a denominator. So I do need to make sure my denominator is not equal to 0. So we need to make sure that x squared plus x minus 2 doesn't equal 0. So I'm going to solve it to see where those bad values are. And I already factored it up here. So I can set my two factors equal to 0 and solve. And in this case, I get -2. And in this case, I get 1. So remember, these are going to be our bad values. So for our domain here, we're going to exclude these values. And I can write it as -infinity to -2, -2 to 1, and then 1 to infinity. Okay. All right. One more thing I want to add in here too before we go on to the next problem is a lot of times you'll be asked to evaluate as well. So plug in numbers. And I'm just going to do this example here, for instance. So let's say I asked you to find f plus g of 1. Well, we can do that, and we can do it in a few different ways. So one way to do it is to just find your f plus g function first, and then plug in the number 1. So you guys know how to evaluate. So if you find that function first, then you can plug in any value that you need. So here it would be 1 squared plus 3 times 1 minus 3. So 1 plus 3 minus 3 is equal to 1. So we can also evaluate these just like we have before. You just find the function first and then plug in your value to that ending function. Another way you could do it is you could actually find the value of one of the two functions individually first and then add them together. So I'm adding because it says add here. So f of 1 is 2 times 1 minus 1, which is 2 minus 1 or 1. And then g of 1 is, let's see, it's going to be 1 squared plus 1 minus 2. So 1 squared is 1. 1 plus 1 is 2 minus 2 is 0. And if I add those together, you see you still get the answer of 1. So I know the problem didn't ask for that, but I want to bring it in there because we do this a lot. So we do ask for you to evaluate a lot of times as well. And you can do that in two ways. So either you can find the ending function first and then just plug that number in, which is often very easy. Or you can find each function individually at that value and then perform the operation. So here it says addition, I would add, but if it asked me to multiply, I would multiply. So you would do whatever the operation is at the end. And both of those are good strategies if you need to evaluate. All right, let's do one more example here. So I have f of x equals the square root of x plus 3 and g of x equals x square root of x minus 2. I'm going to find f plus g here. So I don't want to do all four, I'm just doing one of them. And then I'm going to find the domain as well. So f plus g of x is equal to just f of x plus g of x. Now f of x is square root of x plus 3 and g of x is square root of x minus 2. I actually can't simplify here. These are totally two different kinds of roots. I know they're both square roots, but their insides are different. So you can't combine them together. I can only combine things if I have multiplication or division sometimes, but for adding and subtracting, we just have to leave it. So f plus g of x is actually just the square root of x plus 3 plus the square root of x minus 2, and that's about as good as it's going to get. So you simplify when you can, but if you can't, then you're just going to go ahead and leave it. For our domain here, you want to consider the domain of each of them separately. So if I think of f of x first in my domain, I need to make sure that the inside of the root is greater than or equal to 0, right? I don't want negatives and I don't want imaginary numbers. So I do x plus 3 is greater than or equal to 0. So I have x is greater than or equal to -3. And then for g of x, I have the same kind of restriction, right? I need to make sure the inside is at least 0. So x minus 2 is greater than or equal to 0. and I get x is greater than or equal to 2. Now, for a domain, though, it has to work in both functions. So you need to find the intersection of these two domains. So in this case, it helps to actually just draw a little graph here. Okay. So for this one, we're looking for x values that are greater than or equal to 3. And then for this one, we're looking for x values that are greater than or equal to 2. And I want the values that work for both functions. So I need the intersection. And the intersection is going to be this part right here. So my overall domain is actually only going to be the 2 to infinity piece, right? I can't include this because it doesn't work for G. My numbers have to work in both functions if I'm combining them together. So if you do have restrictions on your domains, then you need to find the intersection of those two restrictions. You need to make sure the numbers work for both functions.